Donc, bienvenue tout le monde à cet atelier de code avec moi IA sur la représentation des mots TALN avec Dessy Aleksandrova.
Hey everyone, thank you for joining us and welcome to our first Code With Me AI workshop of 2022. I'm Janvi, one of your co-hosts, and Maksara has already introduced herself. If you don't already know, Code With Me AI is a monthly webinar series offered by Technovation Montreal, where every month you guys are welcome to join us to learn about a new topic in AI. Last year, we saw some pretty cool topics and themes like deep learning, gender bias in AI, reinforcement learning, machine learning. And this year, we already have a super cool lineup for you guys, and we'll talk more about our future workshops after this one. Tonight, we have Dessy joining us, and she'll be giving a talk about natural language processing, and she's also prepared a super cool coding activity for all of us to try.
Donc, Code avec moi IA, c'est une série d'ateliers interactifs mensuels où des professionnels de l'industrie vous font découvrir des sujets variés sur l'intelligence artificielle. Donc, l'année passée, on a eu des sujets comme l'apprentissage profond et les biais en intelligence artificielle. Et aujourd'hui, on a Dessy qui va nous parler des TALN en intelligence artificielle. Donc, avant de commencer, on a quelques règles Zoom à vous faire respecter. Donc, si vous avez des questions, n'hésitez pas à les poser. Juste levez la main avant d'ouvrir votre micro ou écrivez votre question dans le chat et on va y répondre. Aussi, n'hésitez pas à interagir avec nous avec des réactions ou en allumant votre caméra. On aime ça vous voir. Mais juste, si vous voulez allumer la caméra, sachez que l'atelier est enregistré.
So before we get started, a couple Zoom rules for the night. If you ever have any questions during the workshop, please use the chat and a member of our team will get to you as soon as possible. If you'd like to ask a question out loud, you could use the raise hand button and you could find it right under participants. You're free to use the chat whenever you'd like during the workshop. Please stay engaged with the workshop, and the best way to do that is in the chat. We ask you to please stay muted for the entirety of the presentation, but you're free to turn on your video. Just keep in mind that the session is recorded. Also, to let you guys have the best experience you can tonight, we have a little poll to ask you guys to see which language you would like the presentation to be in. So you could choose English, French, or bilingual. And if you choose bilingual, if everyone likes one language more or prefers one language over the other, we could do it in one language only. But looking at, we will do a bilingual presentation tonight. So after every slide or every couple of slides, we'll switch languages and explain the concepts to you both ways. Perfect.
Donc la présentation aujourd'hui va être en anglais. Donc à chaque la présentation va alterner entre français et anglais. Donc, Code avec moi, c'est une initiative de Technovation Montréal. Technovation Montréal offre un programme, une compétition internationale où des jeunes filles de 8 à 18 ans créent des applications mobiles et créent une entreprise pour résoudre un enjeu de leur communauté. Donc, pour en savoir plus, vous pouvez nous suivre sur nos réseaux sociaux ou visiter notre site web Technovation Montréal.
Awesome. So Technovation Montreal is the program that runs Code With Me, and a lot of you here are mentors and Technovation participants, but for everyone who's new to our community, we are an organization that encourages young women to explore technology and entrepreneurship. And we do this through the participation of a global competition where our participants join other like-minded girls around the world and in Montreal, as well as mentors in business and tech. And they work together over a couple of months to solve a problem using an AI or mobile app project that solves a problem in their communities. So you could give us a follow on all of our social medias to stay up to date with workshops like these and all of other events we post.
Et juste avant de commencer la présentation, on aimerait remercier nos partenaires sans qui on ne pourrait pas tenir ces ateliers. Donc, merci à Google Canada, au MILA, à NextAI, au gouvernement du Québec et à Scale AI pour nous avoir permis de vous présenter cet atelier.
So before we get started, we want to say a huge thank you to all of our partners. Without them, we wouldn't be able to give you these workshops every month, and they've really supported us throughout this whole planning process and in the delivering of the workshops as well. So without further ado, we'd like to introduce you to Dessy. We have a couple of questions. Well, actually just one question for her, and then we'll get started with her presentation. So welcome, Dessy. First off, we'd like to ask you what you're doing now, how you got here, any tips you have for us, just pretty much describe your journey.
Okay, hi everyone. Thank you so much for having me. How did I get here? That's a good question. I guess I'll start with moving, from Bulgaria to Canada, which I did 9 years ago. Yeah, a little bit more than 9 years ago. And I came here with the intention to just continue working as a web project manager. That's what I was doing at the time in Sofia. But then I started learning French because you actually have to be bilingual to be a project manager in Montreal. I didn't know that. So I started learning French, and then French brought me to UDM, where I kind of happened to discover linguistics and really loved it. And then did a major in linguistics and a master's in linguistics. And in the process, discovered more and more about computational linguistics and natural language processing, and the fact that it is nowadays done with modern approaches, with approaches in machine learning and AI. So this was the logical next step for me. So I went and took some extra classes, brushed my maths and stats and STEM in general, and continued with a DSS at Mila in machine learning. And I'm finally done with school for now, I think. It's been a few months that I've been working at CBC Radio-Canada as a machine learning developer with a focus on NLP. And I'm really happy to work on this, on a great project called Moriel, which is a language learning application, actually an application for learning the two official languages of Canada, French and English. It's completely free, and it has original content from CBC and Radio-Canada. So I don't have a slide about it, but I do invite you to go check it out if it's something that might interest you. Donc, je fais un petit résumé en français aussi. Je suis arrivée ici il y a 9 ans, sans pouvoir parler en français à ce moment-là, malheureusement. Mais ça faisait partie de mes objectifs. C'est pour ça que j'avais choisi Montréal, en fait, parce que je trouvais que la ville comme telle était déjà comme un dictionnaire bilingue. C'était très facile si on pouvait parler anglais ou on se débrouillait en anglais de pouvoir apprendre le français tout en étant fonctionnel. Donc, j'ai commencé avec des cours en français, ce qui m'ont amené à l'Université de Montréal, où j'ai commencé à faire de la linguistique. J'ai fini avec une maîtrise en linguistique et d'intérêt pour l'intelligence artificielle, puis l'apprentissage profond. Donc, j'ai continué par d'autres cours, puis au final par un programme offert au MILA, un DESS en apprentissage automatique. Et maintenant, après 6 ans d'études, je suis contente de faire un peu d'argent en travaillant chez CBC Radio-Canada comme développeuse en apprentissage automatique. Et je travaille pour le projet Moriel, ce qui est un excellent projet de CBC Radio-Canada. C'est une application d'apprentissage des 2 langues officielles du Canada, le français et l'anglais, qui est complètement gratuite, puis remplie de contenu super intéressant, original du diffuseur public. Donc, je vous invite à aller la télécharger. Puis enfin, pas besoin de la télécharger, il y a aussi une version web toute nouvelle. Donc, je vous invite à consulter ça, si ça vous intéresse.
Wow, merci.
Ah oui, voilà les liens, merci.
All right, so we'll pass over the control to you, and you could get started on the
Yes.
presentation.
Okay, you guys can see the slides?
Yes.
All good. Okay, I'm just gonna get the chat open. Okay. Great. So, a representation of words in, what do we have next? Oh, sorry, I need to advance a bit. Okay. So word representations. You've probably seen in previous editions of Code with Me how we represent images by numbers. I think there was one class on image classification, but overall we do it fairly easily because each pixel corresponds to a set of 3 values, indicating the amount of red, green, and blue in the pixel. So we can then concatenate all the numbers into a list, a real number vector, and have our vector representation of an image. Donc, vous avez probablement déjà vu des éditions précédentes de Code with Me et comment on représente les images par des nombres avant de voir les mots. Ça se fait assez facilement car chaque pixel correspond à un ensemble de 3 valeurs indiquant la quantité de rouge, de vert et de bleu dans le pixel. Et on peut alors concaténer tous les nombres dans une liste ou un vecteur de nombres réels et avoir notre représentation vectorielle d'une image. Maintenant, qu'en est-il des sons? Now, what about sounds? Sounds are waves, and waves can be converted into numbers by sampling their frequency or their amplitude at, say, equal intervals in time. Those intervals over there. Donc, les sons sont des ondes et les ondes peuvent être converties en nombres en prenant des échantillons de leur fréquence ou de leur amplitude à intervalles égaux dans le temps. But how to transform words, which are strings or sequences of letters, into sequences of numbers? Mais comment transformer des mots, qui sont des chaînes de caractères ou des séquences de lettres, en séquences de chiffres? First of all, let's clarify the need to do that. Okay, so in order for machine learning models to process language, we have to supply them that language in a digestible way. And we know that all computer systems consume numbers. So that's reason number 1. Reason number 2 is that a numerical representation of words is also a way to uniformly represent text and those words regardless of the alphabet or the language that they're written in. And finally, we want to transform words into numbers in a way that encodes their meaning. Alors, tout d'abord, parlons de la nécessité de faire tout ça pour que les modèles d'apprentissage automatique puissent traiter du langage. Il faut leur fournir ce langage de manière digeste. Et on sait que tout système informatique consomme des chiffres. Donc ça, c'est la première raison. Ensuite, une représentation numérique est également un moyen de représenter uniformément un texte ou un mot, quel que ce soit son alphabet ou la langue dans laquelle c'est écrit. Et enfin, on veut transformer les mots en nombres, un chiffre, un nombre, d'une manière qui encode leur sens. C'est très important, ça va revenir tantôt. So, what should these word representations allow us to do? When we contrast and compare word representations, we should be able to say that, for example, cat, the word cat is more similar to the word dog than it is to the word for cow. We would also like to be able to say that cold is the opposite of hot, or that happy has a positive connotation while sad has a negative connotation. And Finally, a final example, among others, is that we would like to be able to say that coffee and cup are related, even if they're not necessarily synonyms when taken in isolation. We also need to be able to calculate the probability of the next word or of a sequence of a word for when we do autocomplete suggestions, for example, of next word, where we ask what is the most likely next word, or when we do speech recognition, where if we're not sure what was the word that was said, we ask the model, okay, what is the most likely word given the previous context? And finally, for machine translation, where the sequence which is most likely in the target language is probably the best translation. Alors, qu'est-ce que les représentations de mots devraient nous permettre de faire? Lorsqu'on oppose et compare des représentations de mots, on devrait pouvoir dire que le mot chat ressemble plus au mot chien qu'au mot vache, que froid, par exemple, est contraire de chaud, et le contraire de chaud, que heureux a une connotation positive, tandis que triste a une connotation négative, et que café et tasse sont liés même si ils ne sont pas nécessairement des synonymes. On devrait également être en mesure de calculer la probabilité du prochain mot ou d'une séquence de mots, parce que quand on fait des suggestions d'autocomplétion, on demande quel est le mot suivant le plus probable. Une autre application, c'est de ces représentations de mots, c'est dans la reconnaissance vocale, parce que si on n'est pas sûr du mot qui a été prononcé, on cherche le mot le plus probable compte tenu du contexte précédent. Et le dernier exemple d'application, c'est dans le domaine de la traduction automatique, où on considère que la séquence la plus probable dans la langue cible est la meilleure traduction. Alors, comment est-ce qu'on peut faire ça? How can we do that? We might wonder, why not represent a word by its definition? In the end, dictionaries exist. So why not use a thesaurus to get these word representations from? Donc, on peut se demander pourquoi ne pas représenter un mot par sa définition. N'est-ce pas? Au final, on a des dictionnaires, donc on pourrait les utiliser pour obtenir ces représentations de mots. But the first problem is that such a representation is not numerical. And we said that we want a numerical representation of words. And we're also defining a word by a bunch of other words. And we can quickly circle back to where we started. I'll show you in a second. Donc, le premier problème d'une telle approche qu'on peut imaginer, c'est que cette représentation ne serait pas numérique. Si on définit un mot par un tas d'autres mots, on peut rapidement revenir au point de départ. Donc, voici l'exemple. If we wanted to know, okay, so word is a type of unit. Okay, what's a unit? Well, unit is a single thing. And thing is an object. And an object is something that exists and can be touched. Okay, what is something? Well, something is a pronoun. And a pronoun, well, it's a word. So you see, we went back to the first word we started with. So let's use a number vector. Utilisons un vecteur numérique à place des mots. But before we delve into words, let's get more familiar with vectors in general, with this example of representing people by number vectors. It's the same thing as describing them with a bunch of parameters, where each parameter adds a dimension to the final description of the person. So we can imagine lots of characteristics of people we can use to describe them. For example, age, height, weight would all be good parameters to use because they're already numerical. But for this scenario, let's use some personality traits, such as being talkative and being adventurous, measured on a scale from -1, like totally disagree, to +1, totally agree. So we have those values for each of our 3 people. And we can have as many traits as we want, but looking at only 2 allows us to plot each person as a point in a 2-dimensional space like this, in a plane, and draw a vector from the origin to that point. So we have the two coordinates per each point, the blue, the green, and the red, and then we draw those vectors from the origin. So unfortunately, we can't plot more than three dimensions, so we're going to keep this example simple with 2 dimensions. Alors, avant de plonger dans les mots, on va se familiariser avec les vecteurs par cet exemple de représentation de personnes par des vecteurs numériques. Donc, c'est la même chose que de décrire ces gens-là avec des paramètres, où chaque paramètre ajoute une dimension à la description finale. On peut imaginer des caractéristiques comme, par exemple, l'âge, la taille, le poids, qui seraient de bons paramètres à utiliser, parce qu'ils sont déjà numériques. Mais pour ce scénario, utilisons des traits de personnalité, tels que le fait d'être bavard ou le fait d'être aventureux. Et puis les deux sont mesurés sur une échelle de -1, totalement en désaccord, allant jusqu'à +1, tout à fait d'accord. Donc on peut avoir autant de traits qu'on veut, mais regardant seulement 2, ça me permet de tracer chaque personne comme un point dans un espace à 2 dimensions, ici, et de dessiner un vecteur de l'origine à ce point. Alors, on peut avoir un vecteur avec n'importe quel nombre de dimensions, mais lorsqu'il va falloir les visualiser, on va se limiter à 2 ou à 3 dimensions, pas plus. Okay. Now that we have people represented as vectors, here are the 3 vectors, we can compare them to find who of them are most similar. If, say, we wanted to suggest them friends, for example. So do you have any guesses, like which 2 persons are most alike among those 3? Donc maintenant qu'on a des personnes représentées sous forme de vecteurs, on peut les comparer pour trouver celles qui se ressemblent le plus, si on veut leur suggérer des amis, par exemple. Avez-vous des idées de quelles 2 personnes se ressemblent le plus des 3 en utilisant juste ces chiffres-là pour les décrire? Okay, I see you 1 and 2. Première et deuxième, ok, et pourquoi? Je pense que ça va être plus long à expliquer. À moins que... Ouais, c'est vrai. True. Here, like, those 2 values are both positive, those are both negative, while here we have 2 negative values. Yeah, that's the right intuition. Les vecteurs sont plus près aussi, exactement. Well, that's the thing. When we work with vectors, we can compare 2 vectors. To compare 2 vectors, we can calculate their similarity using a measure like cosine similarity. So similar vectors point in a similar direction, and their cosine similarity is close to 1. You can see the other 2 options. Like vectors who point in completely different directions have a cosine similarity of -1, and orthogonal vectors are evaluated to 0. So we can see on the graph that the blue. Okay, we can see on the graph that the blue and the green vectors point roughly in the same direction, and indeed their cosine similarity is the largest, just like you guys guessed. So the ability to compare vectors and measure the distance between them will be the key property of vector representations that we're going to use to do all kinds of stuff with words once we've transformed them into vectors, of course. Donc pour comparer 2 vecteurs, on peut calculer la similarité cosinus. C'est formellement ce que vous avez fait dans vos têtes avec ces 2 dimensions. Et des vecteurs similaires pointent dans à peu près la même direction, et leur similarité cosinus est proche de 1. On peut voir sur le graphique que les vecteurs bleu et vert pointent à peu près dans la même direction, et en effet, leur similarité cosinus est la plus grande. Voilà, j'ai une petite flèche, la voilà. Cette capacité à comparer des vecteurs et à mesurer la distance entre eux sera la propriété clé des représentations vectorielles qu'on va utiliser pour faire toutes sortes de choses avec des mots, une fois qu'on les aura transformés en vecteurs. OK, so how can we... ouais, revenons maintenant aux mots. Let's go back to words now. Imagine we had a small bunch of documents, 2 in this case, where each document is a simple sentence. And similarly to the people example, we could try and describe the unique words from these documents. Oops, too early for that. The unique words from these documents by some of their characteristics. For example, we could use the number of letters in a word, the number of syllables. Is it a noun? Is it a verb? Is it an animal? Is it food? So you can see that some of these characteristics could be calculated automatically, like the first 2, for example. But others might require linguists or some tool to tell us if this is a noun, if this is a verb. And others could be completely subjective or depend on someone's decision. For example, is mouse food? Well, depends who you ask. If you ask the cat, it might be, but like, who's to say? So this whole process would be necessarily long, tedious, and error-prone. Disons qu'on avait un petit groupe de documents où chaque document contenait une phrase. De la même manière que pour l'exemple des personnes, on peut essayer de décrire les mots uniques de ces documents par certaines de leurs caractéristiques. Par exemple, le nombre de lettres, le nombre de syllabes, etc. Mais certaines de ces caractéristiques, donc même si certaines de ces caractéristiques, on pourrait aller les chercher, les calculer automatiquement ou aller les chercher dans des dictionnaires ou des ressources, d'autres risquent d'être assez subjectives et ça devient difficile et compliqué de demander à quelqu'un si chaque mot est un animal ou si il se mange. Et c'est surtout très, très... ça peut être rempli d'erreurs, en fait. Ça évite des erreurs. Donc, est-ce qu'on peut faire quelque chose de plus automatique? Can we do something more automatic? Other than that, this is just the same thing, but like represented as a list of numbers. So it has a more vector form. Donc, ça ressemble plus à des vecteurs, mais c'est exactement la même chose que les valeurs qu'on a ici dans le tableau. Alors, comment faire ça plus automatiquement, sans avoir à demander à des experts? Well, the simplest automatic approach to word vectorization would be to associate each unique word. So that's a numerical representation. No doubt about it, but it doesn't have much else going on for it. No information other than the arbitrary IDs is encoded. And we know that words are more than that. Words have meanings. Alors, l'approche automatique la plus simple pour vectoriser des mots serait d'associer chaque mot unique à un ID, puis de créer des vecteurs avec des zéros partout, sauf à la position équivalente à l'ID du mot. Donc, comme je disais tantôt, pour ce premier mot, on va avoir 1 à la première position, le reste, ça va être 0. Si notre mot est un ID 5, ça va être le 1, on va le trouver à la position 5, le reste, ça va être des 0. Alors, c'est bien une représentation numérique, ça, mais il n'y a pas plus que ça qui est encodé dedans. Aucune information autre que les identifiants arbitraires n'est encodée, puis on sait que les mots sont plus que ça. Les mots possèdent des sens. Alors, yes. But if we can't use dictionaries to get a word's meaning from, and if using handcrafted features is too long and tedious, but using indices is too simplistic, then what can we do? Mais si on ne peut pas utiliser de dictionnaire pour obtenir l'essence d'un mot, le sens d'un mot, et si utiliser des caractéristiques prédéfinies est trop long et compliqué, mais utiliser des indices est trop simple, ben alors qu'est-ce qu'on peut faire? Just like with people, where we can tell a lot about a person from who their friends are, Well, we can tell a lot about a word by the words it tends to hang out with, or by its context. Tout comme avec les gens, on peut en dire beaucoup sur une personne en regardant qui sont ses amis, mais on peut en dire beaucoup sur un mot par les mots avec lesquels il traîne, ou par son contexte. Comment incorporer du contexte maintenant dans nos représentations, tout en les gardant numériques? So how do we incorporate context in our word representations? Well, let's first try to use the whole document as a word's context. We define our context as being the document. Okay, we create one row per document here, and as many columns as there are words in our vocabulary. Then we count the number of times a word appears in a document. So first document, the appears twice, we input that and move along. And the vectors we get this way are as large as our vocabulary. The vectors we get this way are as large as our as the number of our documents, as our corpus of documents. So in this case, we have two documents. We have vectors of 2 dimensions only. And to add more dimensions and be able to distinguish between eating and cheese, for example, which right now have exactly the same representation, we'll need more documents. But the more documents we have, the longer the vectors become. So such word vectors, such word vectors fail to capture relationship between words because we look across documents. Our vectors go across documents and do not look at each other or the context, the word context. Alors, essayons d'abord d'utiliser le document comme contexte pour un mot. On se crée un tableau avec une ligne par document et autant de colonnes qu'il y a de mots dans le vocabulaire. Ensuite, on compte le nombre de fois qu'un mot apparaît dans un document. Donc, pour le mot « de », premier document, 2 fois, deuxième document, 1 fois, et ainsi de suite. Les vecteurs qu'on obtient de cette façon, de cette manière-là, sont aussi longs que le nombre de documents qu'on a. Donc, ici, 2. 2 dimensions donc pour ajouter plus de dimensions et pour faire la distinction entre eating, manger, puis fromage ici, parce qu'on a la même représentation pour les deux, on aura besoin de plus de documents. Mais plus on a de documents, plus les vecteurs sont longs. Donc, de tels vecteurs n'arrivent pas à capturer les relations entre les mots, puisqu'on regarde à travers les documents et on ne regarde pas les mots autour. To fix that, we should use the surrounding words as context. So we change this here, our context become words. First, we create a table with as many rows and columns as there are words in our vocabulary. Second, we define a window size, which indicates the number of neighboring words we'll consider. And then we start counting the words a target word occurs with, given our predefined window size. For example, cat appears once in the documents and occurs with the and with is. So we're going to put 1 where cat co-occurs with the and 1 where cat co-occurs with is. The rest is going to be zeros. Mouse appears twice, surrounded by the, and on the left and once by is on the right, because mouse appears here and here. If the window size, oh yeah, sorry. So let's do the chasing now. Can you guys do the last vector? Just to verify comprehension. Oops, there you go. Yeah, we're gonna have 1 at for the and one for is, because, well, chasing appears once and it's surrounded by those two words. Yeah. Donc, pour résoudre ce problème, il faut utiliser les mots environnants comme contexte. Désolée, j'ai complètement oublié de vous poser la question en français aussi. J'espère que vous avez compris ce qu'on faisait. Mais alors, pour résoudre le problème, il faut le problème qu'on avait avant, le fait que notre contexte n'est pas nécessairement le bon, il faut utiliser les mots environnants comme contexte plutôt que les documents. Donc, tout d'abord, on va se créer un tableau avec autant de lignes et de colonnes qu'il y a de mots dans le vocabulaire. Donc, partout, ça va être, sur les colonnes, sur les lignes, ça va être des mots. Et deuxièmement, on va se définir la taille de la fenêtre qui va nous indiquer le nombre de mots voisins à considérer. On va regarder toujours à gauche, à droite, mais un nombre limité de mots. Donc, on dit pour l'instant, la taille égale 1. Ensuite, on commence à compter les mots avec lesquels un mot cible co-occure et en fonction de la taille de notre fenêtre prédéfinie, bien sûr. Donc, par exemple, on a vu que c'est ça, cat, chat occure une fois, qui est entouré par le déterminant, puis le verbe. Donc, on va mettre des 1 ici, le reste, ça va être des 0, et ainsi de suite pour les autres mots. Alors, le problème maintenant avec cette représentation, c'est que déjà, on voit qu'on a la même représentation pour chat, puis pour poursuivre. For cat and chasing, we have exactly the same representation. That's a problem. Un autre truc, c'est qu'on ne peut pas dire qui poursuit qui à partir de la représentation de poursuivre. Parce qu'on voit juste des co-occurrences avec un déterminant et avec un verbe. So we can't, if we take the representation of chasing, we don't know who's chasing, who's being chased, because all we see is that this word co-occurs with a determinant and with the verb is. So what can we do about it? Well, we can increase the window size. We can look for more context. And this gives us now a representation of cat and mouse that reflects the different actions that they're involved in. We can see that the cat is doing chasing, and we can see that the mouse is doing some eating. And we can also see that the mouse and the cat are involved in the chasing, even though from this representation, we could never know who's doing the chasing, who's being chased. You know, this requires our common sense, but like this model doesn't know anything more about it. Alors, si on augmente la fenêtre à 2, les représentations de chat puis de souris reflètent désormais les différentes actions dans lesquelles ils sont impliqués. À l'occurrence, la chasse puis la bouffe. Donc, on sait aussi maintenant qu'un chat et une souris sont impliqués dans la poursuite, parce qu'on les voit ici. Mouse and cat, this should have been red, actually. Mais on ne sait pas qui fait l'action, qui subit l'action, parce qu'on voit seulement cette représentation dans laquelle l'ordre des mots n'est pas du tout encodé. Alors, ici aussi, on obtient un vecteur aussi long que le vocabulaire, et la plupart des valeurs vont être des zéros. So here too, a vector is as large as the vocabulary, and most of the values are zeros. Now, we could ask ourselves, how good are statistical word vectors? On peut se demander quelle est la qualité des vecteurs de mots statistiques. And the answer is, well, not that good. Donc, oui, non, elle n'est pas si bonne, la qualité de ce genre de représentation. When used in autocorrect applications, for example, they often prove to be short-sighted and unaware of the larger context. Lorsqu'ils sont utilisés dans des applications de correction automatique, par exemple, ils s'avèrent souvent myopes et ignorent le contexte plus large. So, how can we create a word representation that is compact, so shorter, more dense, doesn't have all those zeros, is contextualized, and is in general just smarter? Alors, comment on peut créer une représentation de mots qui est compacte, donc qui a une taille plus petite, plus réduite, qui n'a pas tant de zéros, qui est contextualisée et qui en général est juste plus intelligente? Enter word vectors. On introduit les plongements de mots. Drôle de terme en français, j'avoue. A word embedding is a type of word vector, just like the word vectors we saw before, but it doesn't have counts or co-occurrences or even any zeros. Instead, it's a shorter vector produced entirely by a neural net, whose task was to learn, the neural net's task was to learn to predict the probability of a word given its context. Alors, un plongement de mots, on le définit comme un type de vecteur de mots qui ne contient pas de compte ou de co-occurrence ou même de zéro. Au lieu de ça, il s'agit d'un vecteur plus court, produit entièrement par un réseau de neurones, dont la tâche était d'apprendre à prédire la probabilité d'un mot compte tenu de son contexte. And we're going to see how we build a data set for this kind of a model and how we train this model. So instead of collecting documents like we did before, we take a large body of text, say Wikipedia. And just like before, we start looking at each target word and the context window around it. Only this time, instead of counting, we're extracting training examples for our neural net. So here on the right, here we're going, moving along word by word. And here we're collecting inputs, all these 4 words, and an output for each time we move the window along the text. Donc, au lieu de compter des documents, on prend un grand ensemble de textes, disons Wikipédia, et comme avant, on commence à regarder chaque mot cible et la fenêtre de contexte qui l'entoure. Mais cette fois-ci, au lieu de compter, on extrait des exemples d'entraînement pour notre réseau de neurones. Donc, ici à droite, on ramasse dans un tableau les exemples d'entraînement qu'on va utiliser avec leur input en bleu, puis le output désiré. Donc la bonne réponse. Yes, sorry. Ici en rouge. Okay. Now, how to train that thing? And how to get word vectors out of it. Our neural net contains a table with 1 row per word, so as many rows as we have vocabulary items. But this time, we decide the size of the vectors in advance. We control that. The vector is not as long as we have documents or as long as we have words in the vocabulary. So commonly, but it's much, much smaller. Commonly, it's going to be set to 300. So we're going to have 300 columns here. Our vector size is going to be much, much smaller. And given an input of context words, the model aims to assign the highest probability to the correct target word, which we also have. To do so, it adjusts or learns these parameters, example after example. And at the end of the training, those parameters become our word representations. Alors, notre réseau de neurones contient un tableau avec une ligne par mot du vocabulaire. Mais cette fois-ci, c'est nous qui décidons à l'avance de la taille des vecteurs. Donc, ce n'est pas en fonction du nombre de documents qu'on a ou du nombre de mots qu'on a dans notre vocabulaire, mais on peut déterminer la taille du vecteur à quelque chose de beaucoup plus petit. Souvent, on utilise 300 comme valeur. Et ensuite, étant donné un input de mots contextuels, ici à gauche, le modèle vise à attribuer la probabilité la plus élevée au mot cible correct de tous les mots possibles qu'il y a dans son vocabulaire. Pour ce faire, mais il ajuste ou il apprend ces paramètres exemple après exemple. À la fin de l'entraînement, ces paramètres deviennent nos plongements de mots. On a maintenant des vecteurs compacts et denses, donc pas de zéro, mais on ne peut pas dire ce que chaque valeur signifie ou encode, comme on pouvait faire avant. parce que ça correspondait à une concurrence de mots ou une caractéristique ou quelque chose. Donc, pour mieux comprendre ce qui est encodé, il va falloir visualiser ces plongements. So now that we have compact, dense vectors, no zeros, good, but we can't tell what each value signifies or encodes. So to understand more about what is encoded, we'll have to visualize the embeddings. Here's what the 50-dimensional word embedding of the word king looks like. It's simply a list of 50 numbers, and we can't tell much by looking at the values, since those are not really counts or frequencies or anything that we can interpret, but we can compare this vector to other vectors. Voici à quoi ressemble le plongement de mots à 50 dimensions du mot roi. C'est plutôt king, parce que l'exemple est en anglais. Les valeurs vont changer si on avait le mot roi, parce qu'il va falloir changer de modèle. Ça ne sera pas un modèle qui est appris sur Wikipédia en anglais, mais sur Wikipédia en français. Donc, c'est simplement une liste de 50 nombres, et on ne peut pas dire grand-chose en regardant les valeurs, parce que ce n'est pas des comptes ou des fréquences ou quoi que ce soit d'interprétable, mais on peut comparer ce vecteur à d'autres vecteurs. Mettons d'abord tous les nombres sur une seule ligne. Let's put all the numbers on one line. Already a little bit better, although they're so tiny that it's hard to tell or to compare them. So let's color them according to their value. Alors, on va les colorier. On va colorier ces cellules en fonction de leur valeur pour nous aider à faire des comparaisons. If we now contrast the vector for king to the vectors of man and woman, we can easily see how the last two have more values in common, right? They have similarities across multiple dimensions. In other words, the values the model has learned for each dimension encode certain characteristics of the words, but there's no way of knowing what they are exactly, since we haven't specified them beforehand. We just said 300 dimensions, but that's it. We don't know what each dimension stands for. Si on compare maintenant le vecteur de roi, de roi au vecteur de homme et de femme, on peut facilement voir comment les deux derniers ont plus de valeurs en commun. Ils ont des similitudes à travers plusieurs dimensions. En d'autres termes, les valeurs que le modèle a prises pour chaque dimension encodent certaines caractéristiques des mots. Et tout ça, c'est juste déduit des exemples de ce mot en contexte. Mais il n'y a aucun moyen de savoir ce que chaque dimension représente exactement, puisqu'on ne les a pas précisées au préalable. On a juste précisé le nombre de dimensions par vecteur et c'est tout. Le reste, c'est le modèle qui l'a fait. Now, still, we can get an idea of what these dimensions mean, and I should put it in quotes, mean, when we compare different word embeddings, because this is like guessing that we're doing here based on a few examples, but still. So, we can see that there's a straight... on peut quand même avoir une idée de ce que ces dimensions signifient lorsqu'on compare différents logements de mots. Et signification, on le met en guillemets parce qu'on fait des guesses, on ne peut pas être certain, mais c'est quand même intéressant comme exercice. So we can see the straight red column through all of these different words. This simply means that all these, along this dimension, all the words are, the model finds them similar along this dimension. Donc, il y a une colonne rouge à travers tous ces différents mots, ce qui signifie qu'ils sont similaires le long de cette dimension. Maintenant, il y a des sections où... je suis partie en français, mais ouais, je regardais l'anglais. So, there's dimensions where woman, girl, boy, and man are identical, like this one here. Donc, il y a des sections où woman, girl, boy and man vont être, les valeurs sont identiques, comme ici. But there's but there's other sections where woman and girls are similar to each other, but they're different from boy and man who are also similar to each other, like here and here. And then again, yet others when men and women differ from boy and girl. Like here, woman and man are different, but are the same, but they differ from girl and boy who are the same. And here's another example over here. Donc, il y a des dimensions où femmes, filles, garçons, hommes sont tous identiques. D'autres où femmes et filles se ressemblent, mais diffèrent de garçons et hommes. Et d'autres encore où hommes et femmes diffèrent de garçons et filles. Donc, on voit que ces dimensions, certaines de ces dimensions peuvent encoder soit le sexe, soit l'âge, des sens de ce genre-là. So these dimensions probably encode something about gender, and while others encode something about age. Now, all but the last words are words representing people. And we can see that reflected in this dimension right here. We have the same values for all of them except for water. Tout sauf le dernier mot sont des mots représentant des personnes. On peut voir ça reflété dans cette dimension ici, que je trouve ça assez intéressant. Ensuite, here we have, in this dimension, we can easily distinguish some pairs. We can distinguish the pair of girl and boy, then woman and man, queen and king, and water clearly separate from the bunch. Dans cette dimension, on peut facilement distinguer des pairs, des pairs comme reine-roi, garçon-fille, homme-femme, avec l'eau complètement à part. Mais on ne peut pas toujours interpréter ces similitudes, parce que, par exemple, il semble que cette dimension trouve quelque chose de commun entre femme, roi et eau. So, oops, no, next, yes, this one. So we can't always interpret these similarities, though. There's a limit, because, for example, it seems that this dimension right here finds something in common with woman, king, and water. I mean, it's not impossible. We just don't know what. Okay. Now, synonyms and similar words appear near each other in the vector space. Les synonymes et les mots similaires se retrouvent rapprochés dans l'espace vectoriel. But to be able to see that, we project the dimensions of the embedding, say 300 dimensions, into 2 or 3, in this case 3, and we plot them. In this space, we find clusters of similar words because synonyms, antonyms, and similar words appear in very similar contexts in our training examples, you know, in just running text. Alors, pour pouvoir voir que les synonymes et les mots similaires se retrouvent rapprochés dans l'espace vectoriel, on projette les dimensions des prolongements, disons 300, on va les projeter en 2 ou en 3. Et comme ici en 3, puis on trace tous les points. Dans cet espace, on retrouve des regroupements de mots similaires, car synonymes, antonymes et mots similaires apparaissent dans des contextes communs. Now, this being said, where do you think that the word sad, like sad, will be located compared to the word happy? Close or far away? I want to test your intuitions about that. Alors, où pensez-vous que le mot triste sera situé par rapport au mot heureux? Proche ou loin? Okay, we have one guess for far. Do I have a second? Yes, second far, close, twice. Okay. The close will have it. Because, and why? So the answer is close, actually. Counterintuitively, it's going to be close. Exactement. Because they're used in similar contexts. They appear in similar contexts. Alors, ces mots-là, même s'ils sont des antonymes, leurs sens sont opposés, mais ils vont se retrouver proches dans cet espace. Pourquoi? Parce qu'ils occurrent, ils apparaissent dans le même contexte. Just think of like, I'm feeling sad, I'm feeling happy, I was very happy too, I was very sad too, find out something, like all similar context, all contexts in which you can use happy, you can probably use sad. and vice versa. So this kind of model doesn't really help us to deal with antonyms, or to find, to classify words by sentiment or documents by sentiment. Une autre question maintenant. Est-ce que souris sera plus proche de chat ou de ordinateur? Will mouse be closer to cat or to computer? What do you think? In the middle. That's a good call. Computer. Okay, why? You'll have to tell me why. Close to both depending on the document. Yeah, it's just that here we don't have, we've seen the documents, we don't have them anymore, and the positions are fixed of those points. But the answer is we don't know, actually. It depends. What matters is that, yeah, it's not going to be the best position. The thing is that the position of words that have different meanings, such as mouse in this example, each of its contexts, different contexts or different meanings will kind of pull it or push it in different directions, and in the end it won't be as clear, its position won't be as optimal as the position of a word who only has one meaning. It's going to be kind of, that's why in the middle is kind of a good guess. We can say in the middle. Donc, un mot polysémique comme ça, ben, chacun de ces contextes vont influencer, vont jouer sur sa position, et il va se retrouver un peu à mi-chemin entre des positions qui auraient occupé si il n'y avait pas, s'il était monosémique, en fait. Okay, last question. Are we going to have two separate points for duck the animal and duck the verb, to duck or duck the animal? Or in French, est-ce qu'on aura deux points distincts pour les noms? Malheureusement, mon exemple est vraiment pas bon, mais couvent, le nom couvent, puis le verbe couve, les poules couvent, parce que ça s'écrit de la même façon. C'est ça le truc. Ça se prononce pas de la même façon, mais ça s'écrit de la même façon. Donc, quand on travaille avec du texte, tout ce qui s'écrit de la même façon, ça va être la même chose. Alors, on aimerait que non, mais en fait, est-ce qu'on aura, c'est quoi la question? Est-ce qu'on aura deux points distincts? Oui, OK. Puis la réponse est non, on n'aura pas deux points distincts. C'est vrai. Yes, we won't have multiple points corresponding to a word that is to words that are homographed, that are written the same way, because to the model, this is the same word. Like we cannot distinguish those words that are written the same way, unless we apply some pre-processing of our text to identify if the word is a noun and a verb, and to distinguish between those two, for example. Donc, à moins de faire du pré-traitement de notre texte, on ne peut pas distinguer entre le nom couvent puis le verbe coupe. Alors, good intuitions. Now, next slide, please. Okay, let's look at another interesting property of word embeddings. Say we have two-dimensional vectors, two-dimensional vectors, man and woman. Alors, supposons qu'on a deux vecteurs à deux dimensions, homme et femme. If we subtract the vector for man from the vector for woman, we'll get a vector whose direction roughly represents the idea of gender, the difference between a man and a woman. Let's say that let's call this gender. Alors, si on soustrait le vecteur pour homme du vecteur pour femme, on obtient un vecteur dont la direction représente à peu près l'idée de genre, la différence entre homme et femme. Now, if we take the vector for king and add it to and add to it the gender vector woman, man. Maintenant, si on prend le vecteur de roi et on y ajoute le vecteur du genre, femme-homme, femme moins homme, femme moins homme, on obtient un point dans l'espace où on trouve la représentation de. Alors, we get a point here. Click. I have too many clicks. I'm kind of trying to be careful. Yes. We get to a point here. And any guesses which word we might find at this point? Des idées de quel mot qu'on va trouver? Exactement, it's queen. Yes. We find queen, kind of miraculously. Alors, ça signifie que en combinant certains vecteurs de mots, on peut trouver le vecteur en codant la relation entre eux, comme on a fait ici. On fait la soustraction, puis on trouve un vecteur qui a un sens relationnel et ne correspond pas à un mot, plutôt un sens relationnel. Et cette relation tient ailleurs dans l'espace des vecteurs. C'est ça qui est vraiment cool. Donc, on le teste, on l'a testé ici avec Queen, mais ça marche aussi avec tante, oncle, sœur, frère, etc. So what we did here shows us that by combining some word vectors, we can find the vector encoding the relation between those two words. So it's a vector that doesn't correspond to a word, but rather to a meaning, to a relation between those two words and between other words, because this relation holds elsewhere in the vector space, not just between these two. Okay, other examples of this kind. For example, we have, I keep pressing, sorry about that. Okay. So woman and man give us a gender relation. Walking and walked give us a grammatical relation between two verb tenses, for example. While Germany and Berlin, I could have picked another one, give us a geographical relation. Alors, femme et homme nous donnent une relation de genre. Walking and walk, par exemple, nous donne une relation grammaticale entre deux temps verbaux. Puis, si on soustrait Berlin de l'Allemagne, on va obtenir un vecteur qui représente une relation géographique entre un pays et sa capitale. Okay, and finally, one very interesting property of learned word embeddings is that since they ideally model the semantic relations between words, the embedding space that we learn in two different languages will have somewhat similar properties and structure, will kind of look the same. And like people have done this by have aligned one on top of the other, like you can see here. This is actually people at Facebook who did that. And then they use this for translation, for example. But what I find cool is that no matter the language, they kind of, when you bring them down to a cloud of points representing the meanings of their words, two languages kind of look exactly, two different languages look exactly the same. Donc, une propriété que je trouve très intéressante de ces modèles de plongement de mots entraînés est que puisque ces modèles modélisent idéalement les relations sémantiques entre les mots, des sens, donc ils font un peu abstraction de grammaire, quoique, ouais, je ne vais pas rentrer dans ces exceptions et ces détails, mais ils font abstraction de la forme du langage, ils vont plus encoder le sens, ce qui fait que les modèles, ce genre de modèles de deux langues différentes vont avoir les mêmes propriétés, la même forme, la même structure, ou en tout cas au moins très très similaires, tellement qu'on peut les aligner puis utiliser ça pour la traduction automatique ou pour toute autre chose. Okay, so I think this, on a fait le tour. This is the end of what I wanted to show you theoretically on word embeddings and their properties. And pretty much all of these things, we're gonna see them in practice in the notebook. On va voir la plupart de ces propriétés dans le notebook tantôt. Any questions? Yes, I forgot to ask. Well, yes, that's good. Is there anything that would make the vector spaces of languages different? Sure. If you, like this pretty example here, kind of assumes that we train on, we show the model kind of the same text. For example, Wikipedia in both cases, and the Wikipedias should be of roughly the same size and have roughly the same subjects and articles, but you won't get a prettier result if you say take the Bulgarian Wikipedia, which is much smaller than the English Wikipedia, and you try to reproduce this experiment. Although I should have tried that, yeah. But yeah, if you change the training corpus, the text that you show the model, the representations that are learned are going to change. Do we have that's for me. Do we have the link to the notebook?
All right, so if everyone could open up the link to the notebooks. We put 2 links in there right now. One for the English version of the notebook, one for the French version. They're exactly the same activities, it's just the comments are a little bit different in each. So you could open them up, and if you look at the slides that Dessy is showing, we're asking you to make a copy of the notebook in the drive. So the way to do that is to go to File, and then it should say Save to Drive or save a copy in Drive. So once you do that, you'll have your own editable version of the Google Colab activity.
Donc, vous pouvez cliquer sur le lien pour le Colab qui est dans le chat. Une fois que c'est ouvert, c'est important de faire une copie du Colab. Donc, vous pouvez cliquer sur File ou Fichier et ensuite sur Save a copy in Drive ou bien sauvegarder une copie dans le Drive pour avoir votre propre copie. Peut-être une fois que c'est fait, vous pouvez faire un thumbs up ou l'écrire dans le chat.
Okay, so we'll share the links for anyone who just came in, and then Dessy, you could take it away with the activity.
Il faut cliquer sur dans le coin en haut à gauche, Fichier ou bien File, et ensuite cliquer sur sauvegarder une copie dans le Drive.
Okay. You see my screen, I guess?
Yes, we can.
Okay, let me. Is that better?
Yeah, that's perfect.
Oh, yeah, totally. Forgot to put away this function. Oops. I think we're ready.
Perfect. You could just walk through the making a copy for anyone who didn't.
Yeah. Actually, I might do it myself. So file and save a copy in Drive, which automatically creates and opens a copy and renames it. So like this, we're not playing in the same notebook all at once. Okay. Now the first couple of, okay, I'm gonna open. Well, you guys can open the table of contents, but actually I'm gonna close it so that we have more room. Now we're gonna look, in this notebook, we're gonna look at trained word embeddings. We're gonna plot some like we saw in the presentation and then do some stuff with them. The first couple of cells, should have been the first cell, but my bad, should just be executed to load everything we need as methods. And then we're gonna download a pre-trained embeddings, a model of word embeddings with 50 dimensions. Depending on your connection, might take a minute or two. It's 66 megabytes. Yeah, it's those models are, I mean, this is a monolingual model trained on, English Wikipedia, in English only. I wanted to find, I didn't have the time in the end. I wanted to find a French model that was small enough, because you can see this one, it has 50 dimensions, because the 300 dimensional model is normally much, much larger. The only French models that I could find to be able to reproduce those examples were too big to download and to load into memory. So yeah, if I find some, well, you'll have the links to the notebook afterwards, I think, accessible. And we could always add that at a later time. Oh yeah, sorry, I'm totally not explaining stuff like where to click and what to do. It's, as you can see, my first time doing that. So yeah, janvier, or you guys just jump in, interrupt me, say what needs to be said.
If anyone is having any difficulties during the activity, just put it in the chat and we'll help you out.
Okay, but yeah, we click to run the cell here, or we press Shift and Enter when we're in a cell. This does the same thing as well. Okay, now that the model is hopefully downloaded. Oh, je commence à perdre ma voix. We're gonna first do a very simple thing. We're gonna visualize one embedding, and of course you can change this very classical example to something else. Well, at least this. In any case, should give you an array of 50 values. Okay, and now to plot it, as we saw, we're going to use the function plot embeddings, where we give it a list of word vectors. So the model with, we query it like a dictionary. This is one instance, and we could add mots after that if we wanted to. And then here a list of the labels, those labels to print over here. And there you go. Here we have the same thing, but we just the examples we saw in the presentation. Okay. Now, and sure, you can play with a more interesting set of words, try to figure out what those dimensions actually encode by changing some words in the bunch. But here in this section, we're gonna take a look at some word similarities. So we'll see. Yes. Just a reminder for myself. Okay. So using this method, we can use this method most similar that we apply directly to the model. We download it, and we give it a word, and it returns the top n. Again, a parameter to define the closest words to this one in the vector space with their cosine similarity, like we saw. So that's a cool method to just do inspection of words. And for example, look if we can find sad anywhere near happy. Give me a second because we can go at 50. I feel like this is not the same model. Let's just test. No, I think we're good. What's closest to teacher? Yeah. Sorry, I just hadn't explored this example, I guess. Yeah, what we find closest to teacher is student, graduate, teaching, taught. So as you can see, here's examples of, that's why earlier I was like, it's supposed to encode just meaning, but actually it encodes grammar quite a lot sometimes, because we're gonna find similar forms of a word very close to it, or at least plural forms. And for languages, for more morphologically rich languages like French, we're gonna find much more forms of the word, conjugated forms of a verb, for example, being close neighbors of a word, unless we have removed those in a pre-training step, which is what people actually do most of the time. Okay. Now that we've seen how to query query the model and get the closest n words to it. Oh yeah, I had a question here. You notice that immediate neighbors of a word are not all synonyms. And yeah, why they're not synonyms, and where is the actually, which one is the actual synonym? If we use the school definition for synonym. In this group, I personally find only one. Yeah, educator, I think corresponds to my understanding of synonym, while others are similar but in different way. So the point here is that this kind of model, this word representation, this captures, as we saw, all kinds of relations, not just synonymity, because it's not constrained in any way to find different relations in different dimensions. And it has the capacity, it certainly has the capacity to encode different semantic relations between words. Okay, so we can measure the similarity of a word to other words and hopefully get intuitive results. And like at the beginning of the presentation, we said that a good word representation should be able to tell us that cat is more similar to dog than it is to cow. Well, you can test that by just executing this cell as it is. And of course, you can play with like those values because those are inputs, and test other such relations. And hopefully, I put it here, you get intuitive results. It's not guaranteed. But at least for this example, yeah. Okay. Now this is a cell where you can code this example if you feel like it, using, you're gonna need this method. If not, and it's definitely probably something that you might want to do later, we could move on to the following example, where we can use the similarity between words to play the pick the odd one out exercise or game by identifying the least similar word. So here we're using a method called doesn't match instead of similarity of two words. And it should give us cereal, yeah. Between breakfast, cereal, dinner, and lunch. Again, try to test it, try to break it, try to find the model's weak spots. It's always fun. And then ask yourself, why is that? Now, on to the section of, do we have time? How are we on time, Janvier? Do I start the section?
On time. Okay. Actually, quick little activity. Can anyone break that last example? If anyone could write what happens when you change a word.
Yeah, not the code, just the example. So like you separate those words by a comma. That's what the code expects you to do. But yeah.
There is actually, let's try putting a different word. There's something interesting that happens.
Mm-hmm. Do you have an example in mind?
Yeah.
Or were you waiting for some suggestions?
Yeah, change any of the words with like maybe a color.
Like green. And what? Okay, it's my fault this, huh?
So let's see if anyone could debug this.
Good point.
So little
I'm curious now.
You could look at show code and see what's happening.
Mm-hmm. Oh, Jesus. Oh, yeah, because I was doing a test. Hey, the other one is not cereal anymore.
Awesome. So what we did is we replaced the string with the variable input.
Exactly. Here I had hard-coded my initial string, but then we changed it and we put it into a variable, and then this was just remaining the same, the cereal example. Cool. Is it normal that the odd one out is breakfast in your example? Well, I think that it might as well be any of the others. It's just because they don't really form a cluster. You don't have one odd. one that is odd, you have 4 that are odd. So it just happens that for some reason, Germany, bread and cereal are closer together and breakfast is a bit further, maybe because I don't want to say anything about Germany and bread consumption, but I think the model speaks for the fact. Okay, let's take a look at analogies. Like we saw already, what happens when we kind of add a relation that we've computed using 2 vectors, and then we add it to another word. This kind of brings us to another point where most of the time we have the kind of the related word again. Now, those have been used in the past, and actually, yeah, those have been used in the past, let's put it like that, as a way to query models for bias, not just gender bias, but most of the examples are with gender bias, and to kind of prove a point that, well, you know what, those models, they do, they learn a lot of bias, they contain bias, so you should be careful when you use them. And I'm kind of jumping ahead a little bit, and I had everything written out in nicely, but we're gonna go line by line and see that even though it is totally true that those models learn certain societal and human biases because they learn what they see in text, and if the text contains some, well, they're gonna find it, they're gonna learn it. It's not that surprising, but we're gonna actually look at how those people arrive to these conclusions, and the fact that it's not exactly that if you calculate things a bit differently. So let's to find the result of a query like this one, we can use the method most similar that we saw in the previous section, but this time instead of just a word, we need to provide it 2 positive terms here and then 1 negative. So the positive terms are those words that have like a plus sign here in this, let's say, formula, which is, you know, the husband, it's like plus husband plus woman, and then because we subtract man, we put it in the negative term. And yes, I have man here. Yes, totally. Yes, husband and woman are the positive terms, absolutely, and the negative is man. Yes. And if we want to find the top one, the closest point to this new vector that we're forming, well, it's going to be wife. Now, this method, however, excludes the input terms from the results. So we cannot get, even if the closest point was, I don't know, woman or husband or man, we're not going to get it. We're going to get the second closest point. And this might be misleading. So consider this following example, where we have plus doctor and plus again woman, and then minus man. And we seem to be getting nurse. So this looks very sexist already. It's like, okay, wow, so you, like a female doctor is actually a nurse. But before we jump to this conclusion, we could try to do these calculations using another method. Let's first get our analogy vector, which is what we're doing here. We want to take doctor we want to add to it the model of woman, and we want to subtract the model of man. This gives us another vector that doesn't necessarily exist in the space. It doesn't necessarily correspond to a point, but we want to know which is the closest point to it, just like we were doing before with king and queen. So we take this analogy vector and we pass it to the model using the method similar by vector. So we want to see what's the most similar words in the model to this vector that we just created here. And lo and behold, it's actually doctor. Nurse is second. And I did use, okay, I think what I did that, I was probably using a larger model with more dimensions. So you see, I was getting different results. Let's correct that. And this is a good point to make, because the larger the model, the more dimensions it has, the more relations, the more things it learns, the more things it encodes, and the more precise it is. So you do want to work with a larger model if you can. It's just that here to speed things up and to be able to print those cute, colorful vectors of 50 dimensions instead of 300. It was just more appropriate to use the smaller model. So here, but still, the important thing is that nurse is second. And the cosine similarity is 80.84. Okay. And this makes sense when you think about it, because doctor is not a gender term. We don't have a female version, a male version, like a husband and a wife. We don't have two different words. For a female doctor, we still use the word doctor. We don't call female doctors nurses. So we should expect, and as expected, we do get the result that the closest to doctor when we add a woman and we remove a man is still a doctor. Okay, and here we can do some tests to see further what's going on. And if this theory of, okay, it's because we have gender terms and then we have professions and the professions are not necessarily gendered, then we're not going to get the same results. And yeah, feel free to add more examples here. You can, like, any gendered, like the male version of any, I don't know, uncle, brother could go here, etc., etc. And same for professions. But if we execute that, I take the top n, so the closest point to this new vector that we get if we add woman and remove man from any of these words. So with husband, a gender term, we get wife. Exactly. Father, we get mother. We don't get father again. Mother is first. For boyfriend, girlfriend is first. For king, however, queen is second. King comes first. Now, I don't know, I have a theory about why that might be. But it's nothing that I can prove to you. But I think that what's going on here is that it's a question of frequency in our training corpus. And if such gender terms like husband and wife and father and mother, we don't have a reason to think that one is more common than the other. Well, we surely know that in Wikipedia, there's more kings mentioned than queens. That's like, oh, for brother you get, for brother you get daughter. Interesting. Well, there's quirks for sure, unless it's we make sure it's not the code that is the reason. But that's yeah, that's one example that I haven't tested. So I think that what plays here in this example, even though we have female, male and a female like term, for this thing, the different frequencies might play a role. That's why our vector kind of stays close to still to king, doesn't go closer to queen. But for the professions such as doctor, programmer, engineer, teacher, we get the same thing when we add the gender vector. So they should tell us something about bias. Okay, I think I mentioned all this. Here's a link to the paper that first talked about that, kind of debunked this whole, oh, models are biased, and let me show you how by these analogy examples. It's not, again, it's not that they're not, but it is a bit harder to prove it and to show it than it would have been with just these examples. And here I think is the, no, that's not the last section. We have a section on other types of analogies that you can play with. And I already give examples here with stuff that works and stuff that doesn't work. Again, for some of them, I kind of have a theory, but that's it, just a guess. For others, I don't have a clue. But for example, the first one, the country capital. What I find that works is Italy, France, India, Bulgaria, Serbia, Poland, China. So you see, there's no, it's not a, the examples that work are not necessarily big countries or small countries or European countries, or, you know, I try to diversify it a little. But those that did not work for me were countries where the capital is actually not the larger city. It's not the most popular city. So maybe that plays a role in this case. But you should definitely test it with more examples before you can make a conclusion. Yes, one thing I wanted to mention in all these games of analogies is that what seems to be quite important for them to work is to properly calculate the relation vector. So to properly calculate this relation vector, when we're gonna take one vector out of another, we want to get a representative example of this relation. That's why for the gender vector, working with woman and man makes the most sense. Even though we could maybe get somehow similar results if, say, we took daughter and son, which should entertain the same relationship between each other, but women and men are just the classical canonical examples, the more frequent, etc. So in this case, choosing the right capital, German, a pair of like country and capital, definitely plays a role in how good of results you're going to get. So this is something that could be improved if you choose the better pair for your relationship. Here this is an example with past tense, present, progressive tense, which again works for some verbs, not for all of them. That's an example that we didn't see in the presentation. You can go from an adjective, what do we call this form of an adjective, to its superlative form. And here I'm using high and highest to kind of give me this example of relationship. And for bright, I guess for bright, it doesn't work. For fast, fastest. Yes, we're gonna add bright here. Okay, and of course, you can imagine all kinds of analogies. the sky's the limit. Okay, final thing I wanted to talk about is text classification. And janvier said that the next activity code with me is gonna be a text classification. So this is like really small. Like you're not gonna see this kind of text classification next time for sure. So this is a very rudimentary example of how we can use word vectors to do text classification, and especially on what are the limits of this method, because it's very, very limited. But it's interesting to see if we can see how and why. Now that we've kind of developed an intuition of how those models works and what are the strong suits and their weaknesses. Okay, so I have here 4 articles. It's actually very long sentences, like sentences that I took from Wikipedia on 2 different subjects. On machine learning and artificial intelligence, that at the end I lower everything and split, because that's how we find our words in the model. They're lowercased during the pre-processing. And then there's 2 documents on mushrooms. Okay, so I made sure to have 2 reasonably different subjects, because everything else is very small. We have small documents, we have small corpus, etc. Now, to get a representation, because we have a model with word representations, right? But now, how do we represent an article or like a sentence? Well, one very, very, very simple way that we can do that is to sum the word vectors of each sentence. And this way we get to sum them or to average them. And this way we get a sentence vector within the same dimension. So we just lump them together. And then we can compare those sentence vectors between them using cosine similarity. So let's do that for these 4 documents. And we get the similarity of each document to the first one. We compare each one to the first one is, well, not surprisingly, 1 with the first one because it's the same. Very, very high with the second one because it's the same topic, the same subject, the same vocabulary basically. And then lower values, lower similarity, smaller similarity with the other 2 documents. So we get what we expect to get. Good. Why does this work? Well, because like I said, I made sure that the topics or the subjects are quite different so that they use different words. And I made sure also that the subjects are quite technical so that they have, words, uncommon words that might appear oftentimes in this domain, but will never appear in this mycology domain, like, I don't know, woody climbers and shrubs and fungus, etc. Okay, but what if we tried this on more classical, on something that we try to do oftentimes in NLP, is to classify reviews in positive and negative. It's a very real world problem, although this one is, if our task was if we had like a bunch of articles on different subjects and we wanted to find subjects, we wanted to find the articles that are of interest to us. Say we're interested in machine learning, where we're going to give one example and then go and fetch all the closest documents that our model is gonna provide to kind of filter those out of the corpus. But if we had reviews, was my point, and if we had 2 positive reviews and 2 negative reviews, that are formulated in a very similar way. And we tried to use sentence similarity to find out, to kind of group the positive ones and away from the negative ones, just like we did here. We get an error, of course, okay. We get that I hated this movie is very similar to I love this movie. Why is that? I mean, I think everyone knows the answer to the question at this point, but still, 3 words are the same, sure, and not only 3 words are exactly the same, and what about the different ones? Because it could have been enough, one very different words, like say intelligence and fungus, might have been enough to distinguish those, to kind of push those representations apart. But the thing is that I hate and love, even though semantically for us they're like opposite things. Exactly, for word embeddings, for a word to vec model, they're the same thing. They're very close together because they appear in similar contexts. That's exactly the example, exactly the same. You can substitute hate for love and your phrase will not change, will still be correct. So they do appear in similar contexts, so they end up being close together and they are considered just similar, just like synonyms are considered similar. So this is a problem if we want to compare similarity of this kind of documents, where it's nuances. It's one word that's going to make the difference instead of a whole vocabulary that is going to be different. Because here people are going to talk about the same things. It's all about movies. There's no other topic. And the one word on the opposite or the other one, yeah, opposite. But as long as the model is concerned, they're very similar. And then the other 2 examples are further away because they're phrased differently. They use different words. Yeah. So I think that ends our journey.
Yes.
Unless there's other questions.
Huge thank you to Dessy.
Thank you.
Merci, Dessy. So our virtual round of applause.
Thank you. Un atelier vraiment intéressant.
Mm-hmm. And thank you to all of you for joining us. If you would like to come to our next workshop, we are hosting our second Code With Me AI of the year on February 17th. It's actually part of the Mois numérique jeunesse by Printemps numérique. And as Dessy hinted, we will be dealing with classification of texts and of images. So stay tuned for our big launch of that on our social media, and you have all of our social media handles here to follow us.
Donc, merci à tous d'avoir participé à cet atelier. On va avoir notre prochain atelier, c'est le 17 février. L'atelier fait partie de l'événement du printemps numérique, le mois jeunesse numérique. Et comme Dessy a dit, ça va parler d'images et de classification. Vous pouvez visiter notre site web pour plus d'informations sur le programme Technovation et nous suivre sur les réseaux sociaux. D'ailleurs, on a posté des stories sur Instagram. Vous pouvez aller y réagir et nous donner du feedback sur l'atelier d'aujourd'hui.
to answer a question in the chat. The slides and the recording of this workshop will be available on our website by next week. So stay tuned, and you'll be able to see the recording and slides on technovationmontreal.com. So one last thank you to all of our partners who made this workshop and all of our next ones possible.
On voudrait remercier une dernière fois nos partenaires qui nous ont permis de vous offrir ce merveilleux atelier.
And if anyone has any questions for us or for Dessy, the floor is open. And one last huge thank you to Dessy. This workshop was incredible. I loved the activity. Overall, great.
Thank you guys for the opportunity. Excuse me.
Go ahead.
I wanted just to thank you guys for the activity, all your work you're putting into that. It's amazing. Yeah, very nice initiative.
Merci beaucoup, Dessy.
So Dessy, we have a question for you in the chat. Do you have any online courses or reference books that you would recommend to have a deeper look into neural nets or machine learning?
Yes, definitely. And I wanted to have a slide on that, but we will instead put those links on Technovation's website, right? Yes. Together with the video?
Yes, all of the resources that Dessy will share will be part of our website, and for all of our participants, we'll send you the link to the recording, the resources, and the slides as soon as everything's online.
Oui, je vais vous partager des ressources pour débutants, des choses cool, accessibles, puis intéressantes, espérons. And stuff that I inspired some of the information from, like that, you know, that I've read myself to improve my understanding. So yeah, definitely.
So we'll stay on the call a little bit longer if anyone has questions. If not, have a great night.
Thank you. Can I ask a question?
Yes.
Well, I have a question for Dessy. I really found interesting your journey, and then how you took, well, I'm a mentor at Technovation, and how you took linguistic and you use it into machine learning and into artificial intelligence. But the question I have is, when does the bubble light happen? When did you know that you can connect the two dots?
Mm-hmm. Well, kind of when I found out that to do computational linguistics, you actually need to do it with AI and with NLP. That nowadays it's not done with other methods, with more classical linguistic methods, should I say. I mean, I'm very glad that I kind of took this road and went through linguistics, but I must say that a lot of people who end up in NLP, natural language processing, or traitement automatique du langage naturel, TALN, do not necessarily go through linguistics or like take a few linguistics classes on the side, and they're more focused on the engineering part or more on the machine learning part, and this is great, but it's useful to have. I mean, of course, I'm going to say that, but it's useful to have, if you're going to be working with language, dealing with language, it's useful to have the intuitions and the knowledge of a linguist. And as a linguist, I can say that it was, and it still is a challenge to kind of learn on the side all the engineering and computer science and mathematics and statistics that is required to do NLP. But it's so it's too yeah. I would have taken the other road, like go into computer science, had I had I had like a mentor earlier in life, probably, or like an activity like this, you know, someone encouraging me to go into to go into computer science earlier. I totally admit that I've always entertained the idea, but kind of never dared until I actually ended up getting there, but like taking the long road.
Okay, so it's thank you so much for sharing that. The reason why I'm asking is because I studied mathematics myself in computer science, and then I studied in English, and I took some linguistic class in French, but I never connected the two dots. That's why, I never connected the two dots. I don't know if I didn't connect the two dots because it was back then in 2011 or in 2010. There were maybe artificial intelligence was not like the buzzword as it is today.
Yeah, actually, NLP, like this whole idea of word representations, word embeddings, when this, I think it kind of created a revolution, a small revolution in NLP, and brought so many people into the field, and like so much research. But this happened like what, 2013 to 15?
Yeah, exactly.
You know, yeah.
Yeah,
So,
because I was in school 2000, like I was doing computer science, mathematics, and linguistics around 2009, 2008, 2010, around that area. So I guess it wasn't the buzzword. So I never really connected the two dots. Now that I'm seeing, I'm like, oh my God, like I could have connected a long time ago. It would have saved my time and so many things. But it's really
not lost. Yeah, if you've seen those notions, it's not lost. I mean, you can always, once you connect the dots, then
yeah. Thank you so much for sharing your experience. I really enjoyed that presentation, and wow, it's amazing.
Thank you.